glad to present this work on registering multiple point clouds using learning methods. This work is in collaboration with Jean Gocic, Saifa Zhou, Jan Wagner, and Leo Gibas from Stanford University and ETH. Okay, so essentially what we are looking into is some form of a structure from motion problem, right? That's a slight alternative to this. So in such a scenario, we would estimate normally some pairwise information between images, right, that relates those images, and then estimate camera poses, and from that, estimate the 3D reconstruction. That would be a classical structure from motion scenario. Now, we will do it with point clouds instead. Right, so this is slightly different in the sense that the 3D data would not have to be inferred from the images, but it is there. However, the alignment and the relationships between those in presence of clutter and occlusion is quite a challenging problem. So we study exactly this problem, right? Given a bunch of unordered, unstructured point clouds that we assume to have partially overlap, we are seeking for a globally consistent alignment of all these scans. And of course, in the context of this workshop, we present a deep declarative network to do so. Well, this is a pretty classical problem, I would say. It started actually in '99 when Tully at Stanford was trying to work on the Michelangelo project. Right, and then it leaped into multiple groups working on multiple problems, multiple sub-problems, let's say. And many of those devised great algorithms for registering multiple point sets. And the research still goes on. So that there are probabilistic formulations, works that use priors, or even more based on the Lie algebra. And yeah, so many works exist in this domain. So from a classical perspective, we are looking into two problems. One of those is pairwise registration. So we just have all those scans, the S, and we are registering those scans with each one with the other one, right? And the second stage is basically a global refinement. And in that stage, we take all this registration information and try to globally fuse that into one coherent whole. And we see here two decoupled optimization problems, actually, right? And our goal is basically to come up with an end-to-end algorithm to do this within a neural network. So let's look at these two problems now. So the pairwise registration is given 2 point clouds. We are seeking a rotation matrix and a translation vector. So rotation is in the spatial orthogonal group, and translation lives in a Euclidean space. And we like to minimize this energy, which is a basic iterative closest point energy, actually. So if the points are under correspondence, it's just R times Pi plus T minus let's say, the corresponding point. And how to estimate this corresponding point has been an issue, and is a very well-studied topic. So in many scenarios, of course, this is kind of an argmax problem where we are required to pick one correspondence so it's kind of like a bijective map even, I would say. However, for implementation in networks, this is not really nice. So many people, including us, would replace this with a stochastic correspondence, in the sense that one point is assigned to multiple other points with certain probability rather than a single one. Right, and this allows for a differentiable solution, basically. So we minimize this energy just by replacing this phi and by a classical minimization scheme. And of course, since we have that now, what we could do, we could further compute certain weights, and this would kind of allow us to have correspondences plus related confidences, basically, that we do by a confidence estimation block. And of course, we could now use different losses, for instance, a classification loss on correspondences, and the transformation loss, because we know the ground truth transformations during training. We have such data sets now, even real. And the confidence estimation block is implemented as a neural network and comes on top of this registration result, features from the registration result. Okay, the second stage is global registration, and we handle this by what is called the synchronization of poses. And there is a CVPR tutorial actually today that we are also holding in this sync-in-vision.github.io link. So it is basically, the synchronization is defined to be finding simultaneity or coordinating events to operate a system in unison. So what would that correspond to in our scenario? Well, we have such a scenario, right? We have multiple cameras, and then we have a 3D scene. And from those cameras, we could speak of a pose graph, right? We could compute such a pose graph because pairwise relationships kind of imply that. And then we could, through some confidence estimation, so we could first, of course, compute the pairwise registration and then cut certain edges. Then this is completely heuristic currently. And then, and then we could use some kind of a consistency constraint to make sure that this graph is coherent as a whole. And the goal is, of course, to estimate the world transformation parameters of these cameras, basically rotation and translation, with respect to one frame, which can be chosen arbitrarily in many cases. So synchronization has been applied to many, many domains. It's from structure from motion to 3D shape matching, even segmentation. So that's a very well-studied domain, but implementing synchronization within a neural network maybe is not that straightforward. There are only a couple of works, and we choose one of those. That the spectral clustering algorithm allows for a differentiable synchronization. So we have a degree matrix, and we have this this is basically like an adjacency matrix, but composed of rotations inside, and this d minus a would give us some graph Laplacian where the maps or the values or the labels of the edges are group valued, let's say. And if we solve this problem under the spectral relaxation, we can take the eigenvectors corresponding to the smallest eigenvalues of the Laplacian and then project the result back onto SO3. And the translations would follow a similar trend in Euclidean space. Now we can have an end-to-end solution, right? Because now we have the pairwise registration and synchronization put into differentiable forms, and now we can stack them and have an end-to-end network, and then iterate maybe even this registration a couple of times in order to come up with an algorithm that is IRLS-like, iteratively reweighted least squares-like, so that the system is a little bit more robust. Okay, so this is the method. And how would the results look like, right? What are the improvements coming from doing that? So first of all, we can improve the pairwise registration, right? So with respect to a standard baseline that is fast global registration, which is pretty standard now, and to all the other pairwise registration algorithms, even deep networks, we can improve that. And that comes because of the powerful features, the FCGF features that we use, and second, because we are training it end to end. And then we are, of course, doing multiple iterations, and you can see the improvement in the table presented here. Right. So we can then go to the multiview registration setting where we can take scannet scenes and try to align them. Right. There's a nice ground truth for that, so we can compare our methods. And we see that, first of all, compared to pairwise registration methods, having a globally consistent alignment and an outlier filtering are crucial in getting good results. And in all of these, the best results are attained by a network that performs a synchronization on top of it. So we can also see some qualitative results. And you can see that on 3D Match, the state of the art, that is the SE3 EIG, that's a synchronization solution as well, and uses our features. But not differentiable, well, not at least an end-to-end pipeline. And you can see that there's quite a bit of improvement with respect to that. And we are pretty close to the ground truth. And these results, I would say, are not really cherry-picked. We have many, many examples of that. And the same holds true for different scenes. Yeah, so this will be the end of my presentation. And we are making the code online. So the first stage of pairwise registration is already online, and the second stage is coming hopefully along these days, maybe after CVPR. Yeah, and you could also visit the tutorial on synchronization in Vision to get more information. Well, thank you.